Hey guys, this is Anas Hamoudni from Math World and welcome in this new video. The video of today will be about the proof of the infinity of prime numbers. So there are infinitely many prime numbers. So let's start. First, let me free some space here. And we start by defining two main things. First, let's define what a prime number is. Well, basically a prime number, let me just write here, a prime number is actually, let's call it P. A prime number P is basically two main things. It's a natural number, which is not equal to 0, so bigger than 1, and P has only two divisors. So only two divisors, which are 1 and P. So only 1 and P divide P. Divide P, actually. Sorry. So, for example of a prime number, well, we can add, actually, example here. Well, 2 is prime. Because 2 has only two divisors, which are 1 and 2. So 3 is also a prime number. 4 is not a prime number because 4 is divided by 2, which is not 4, neither 1. 5 is a prime number. 7, 11, 13, etc. So the second thing that I want you to define is called the fundamental theorem of arithmetic. Fundamental theorem, called it TH, of arithmetic. The fundamental theorem of arithmetic actually states that for every integer which is not equal to 0, where integer which is bigger or equal to 0, not equal, sorry. For every integer which is bigger than 0, this integer, we call it n, is equal to product of primes. So this is the fundamental theorem of arithmetic, and we're going to use it in this proof. So let's start now the proof. Well, the proof actually, it's based on a contradiction. So we're going to assume the negation of the theorem. Well, the theorem that we're going to prove is that there are infinitely many primes, and we'll assume that actually there is a finite number of primes. So let's call them Q1 to Qn, and we assume that there are n primes only. N primes only. Now, if there are n primes only, let's take the following number I'll call it Q, or big Q, so capital Q, and we'll take it equal to the product of all primes that we are already assuming plus A1. Well, this Q is bigger than all. Well, this is strictly bigger. So let's just remove this or equal to. This is strictly bigger than all the QI's, which are the prime numbers which are already assumed. So I is from 0 to n. So capital Q is bigger than all of them, and we assume that this capital Q is not a prime. So assume that capital Q is not a prime, which means that following the fundamental theorem of arithmetic, which is actually defined here, for every integer, including capital Q, Q is equal to a product of primes. So it has a prime divisor, which is not equal to Q, because Q is not a prime, and which is not equal to 1, because now 1 is not a prime. So since there's a finite amount of primes, which are this Q1 to Qn, so Q must be divided by one of these Q's. So let's assume that Qj, let's assume that there is a J, such as Qj divides Q, which means which is equivalent to, there is a J such as Q is equal to Qj times a certain number k, with k it's an integer which is not equal to 0. So now we know that Q is equal to Qj times k, and we also know that Q is equal to the product of all Q's plus 1. Now, by making the equality between the two forms, so let's write it in green maybe. Qj times k is equal to Q1 times Q2, Q times, including Qj, times all Q's until Qn plus 1. So this is the equality which we have now, assuming that Q is not a prime number, and assuming that Q is equal to the product of Q's plus 1. Let me just now get here to this page. So now we have the equality, and let's now continue our calculations. So basically, if we factorize by Qj, we'll have k minus the Q1s until, well, let me just correct this, times, well, Qj minus 1 times, well, we'll not take here Qj because Qj is already in the outside. So we'll start by Qj plus 1 until Qn this is equal to 1 actually. So now, what we have here is a prime number q, j, which is equal than 1 strictly, times another integer, or maybe, well, it's not negative integer, this k minus this whole thing. It's not negative because the product of qj by a negative number will not be equal to 1. So this part here, this whole part here, is bigger than or equal to 1. It's not 0 because 0 times qj is equal to 0, which is not the case here. So we have something bigger than 1 multiplied by something bigger than 1, where something here is strictly bigger than 1, times something bigger or equal to 1, which is equal to 1, which is actually impossible, because something here is strictly bigger than 1. So this product should be strictly bigger than 1. But we found that it's equal to 1. So this is the contradiction. So this is the contradiction, and that means that our hypothesis since the beginning is false for Q. So Q, capital Q, is actually prime. Because this is a contradiction. So this form here is not possible to be true. So it's not true. This qj times this equals to 1 is not true. So capital Q is prime, and we already know that capital Q is equal to the product of all the p's, so plus 1, which is already bigger strictly than the biggest p, which is Pn. So Q is the prime and is bigger than the biggest prime that we already assumed. So Q is a bigger prime. So what we found here is that by assuming that the set of prime numbers is finite, we found a number which is prime and which is bigger than all the primes that we assumed in the first place. And this already is another contradiction, and it proves that our assumption was wrong actually, and that the set of prime numbers is infinite. So the set of primes is infinite. So this was today's video. Thank you for watching, and goodbye.